I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology, and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and RStudio for the geostatistical analysis and graph design, and with Quantum GIS for the final map edition. We are going to compare the results we get with the geostatistical analysis extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but RStudio and Quantum GIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I am going to be talking about exploratory data analysis, experimental semivariogram, model semivariogram, cross-validation, Kriging interpolation, and also, at the end, we are going to be working with the map edition with Quantum GIS and also reporting results. This is the 10th video of the Geostatistical Analysis course, and the topic for today is the model comparison. We are going to be talking about what are the differences for the three more popular Kriging models. It's going to be a very short introduction about the ordinary, simple, and universal Kriging. But also I am going to recommend some YouTube video channels that you can use as a very important source of information if you want to go deeper on the understanding of Kriging interpolation. Also, we are going to see how to calculate the model of a semivariogram for anisotropy. I know in a previous video we was talking about it, but a subscriber provide me some information to improve the experience using ArcMap, and now I believe we can make a better job. Also, at the end, we are going to be talking about the model comparison using Quantum GIS. I am going to create three different compositions. One for a raster images, another one for the mix of raster images and also vectorial layers, and also the last one is going to be related just with vectorial layers. Okay, let's go to do it. At the previous video we saw how we can use the script in RStudio to make the universal Kriging interpolation. Also, we created three different kind of maps: the predicted values, the variance, and the standard deviation. First, we did in latitude and longitude, and later in UTM coordinates. We also created a map with contour lines. We learned how to export the maps from RStudio to a GeoTIFF format, and then we opened the file in Quantum GIS. We was working on the Kriging interpolation on ArcMap for a directional and omnidirectional semivariogram models, and we created some maps. At the end, we was talking about how to export a geostatistical layer from ArcMap to a raster file, and then we open the file in Quantum GIS. Remember that if you missed that video, you can hit the card located at the top right corner of your screen. Today I am going to start with a very short introduction about what are the different Kriging models, and I am going to talk about the three more popular: the ordinary Kriging, over here, the simple Kriging, and also the universal Kriging. And I'm going to use the website from ArcGIS desktop. I'm going to leave the link at the video description. These explanations are going to be very simple because I don't want to go deeper on the mathematical part of the Kriging interpolation. That could be something really complex that it's out of the goal of my videos. I prefer to be focused on the practical side of the Kriging interpolation. However, if someone is interested and wants to go farther and deeper at the mathematical part of the Kriging models, I would like to recommend 3 YouTube video channels. I'm going to leave a card at the top right corner of your screen for each of these channels. The first one is going to be the Geostat Guys Lectures. The author of this channel is Michael. Michael is a professor at the University of Texas, and the topics for his lectures are research and data analysis, geostatistics, and machine learning, and he has a lot of videos. And he also updates the channel pretty often, loading new content. As you can see, the last one, it was 1 month ago. And as you can see, he has a lot of videos. The second channel is going to be the Geodata software. The author for this channel is the Professor Luke Anselin at the University of Chicago. And the topics for his lectures are exploratory data analysis. Also, he has a lot of videos, and the channel also updates pretty often. As you can see here, the last videos are from 5 days ago. Then the last channel is going to be from Edward Isaacs. And there are just a few videos, as you can see, but these videos are really well explained and very easy to understand, and it's really good source. The problem is this channel was updated 5 years ago and there is no more videos, but these ones are really good. Then let's go to talk about ordinary Kriging. Understanding ordinary Kriging. Ordinary Kriging assumes this model, where Z is the variable of interest, S is the location, mu is the unknown constant, and epsilon is the error or residual values. One of the main issues concerning ordinary Kriging is whether the assumption of constant mean is reasonable. Sometimes there are good scientific reasons to reject this assumption. However, a simple prediction method, it has remarkable flexibility. The following figure is an example in one spatial dimension, where at the x-axis we have the x coordinates, and for the y-axis we have the measured value. It looks like the data is elevation values collected from a line transect through a valley and over a mountain. It also looks like the data is more variable on the left over here, where the dots looks like more randomly located, and becomes smoother on the right over here, where it looks like there is a trend here. In fact, this data was simulated from an ordinary Kriging model with a constant mean mu, this one here. The true but unknown mean is given by the dashed line. Thus, ordinary Kriging can be used for data that seems to have a trend. There is no way to decide, based on the data alone, whether the observed pattern is the result of autocorrelation among the error epsilon with a mu constant, or trend with a mu changing with the s. Ordinary Kriging can use either Semivariogram or covariance, which are the mathematical forms to use the express autocorrelation, use transformations and remove trends, and allows for measurement errors. The important things for this text are Kriging model with a constant mean. For ordinary Kriging, we are assuming a constant mean. And this constant mean is unknown. And also, we can use semivariograms or covariance for ordinary Kriging. And also, do the transformations, remove trends, and also calculate the error. Now let's go to move to the next one, that is going to be the simple one, and it's going to add more explanations about ordinary Kriging. It's going to clarify a little bit more what is ordinary Kriging. Then simple Kriging, understanding simple Kriging. Simple Kriging assumes the same model as before, but in this case mu, it's a non-constant. That's very important. For example, in the following figure, which use the same data as for ordinary Kriging and universal Kriging concepts, the observed data is given by the solid circles. It's these black circles over here. The non-constant represented by the dotted line, it's mu, as before, this line over here. This can be compared to ordinary Kriging. For simple Kriging, because you assume that you know the mu exactly, you also know the epsilon error exactly at the data location. Then as we know this mean for our data, we also can calculate the difference between the mean value to this point over here, because we know the data here and we know the data here. Then we can make the difference and get the epsilon. That is going to be the residual. For ordinary Kriging, you estimate mu, so you also estimate the epsilon. If you know epsilon, you can do better job of estimating the autocorrelation than if you are estimating the epsilon. The assumption that you will know the exact mean, mu, is often unrealistic. However, sometimes it makes sense to assume that a physically based model gives a known trend. Then you can take the difference between the model and the observations, called residuals, and use simple Kriging on the residuals, assuming the trend is the residuals is known to be zero. Simple Kriging can use either semivariograms or covariance, which are the mathematical forms to use to express autocorrelation, use transformations, and allow for measurement errors. Then the important things for the simple Kriging is that the mean is known, also is constant, and simple Kriging can use semivariograms or covariance, and also we can use transformations, and it allows us to calculate the error. Now let's go to see what it represents with our data. Then let's go to here, ArcMap, Geostatistical Analysis, Explore Data, and let's go to plot the histogram. Then let's go to select the parameter we want, it's groundwater. As you can see, our data is quite normal distributed. The mean and the median has pretty similar values. The mean is 93.554, and the shape for the accumulative curve is going to be a kind of bell. Then if you want to apply simple Kriging on this data, you are going to assume that for all the area, the mean is going to be 93.554. But that is not true, because that's the mean for our data exclusively, right? That's the point. What here it says, the assumption that you will know the exact mean, it's often unrealistic, because what you know is the mean of your data, but not the whole area. However, if you have an area where the density of the observations or samples are really close each other, and also the variability is very low, you can assume to use a simple Kriging, because as we said previously, as you know the mean, then also you know the location of your data, and you make the difference and you can get the residuals. And with that value for the residual, very realistic, the predictions also are going to be really realistic. But you know, to use simple Kriging, it's a very exceptional way to do Kriging interpolation, and it depends on many variables, right? As I said, what is the density of your sample or observations, what is the variability, and etc. However, when we are using ordinary Kriging, we don't need the mean. As you can see, for example, here, if we go here, select your data over here, Kriging, co-Kriging. Next, if we select simple and we select logarithmic transformation, for example, as you can see here, the software calculates automatically the mean of your data and it places the value here, right? But that's the mean for your samples. But if you choose, for example, ordinary Kriging, even if you apply for logarithmic, it doesn't ask for the mean of your data, because you don't need to know what is the mean, as the mathematical model is going to predict what is that mean. But in both cases, simple and ordinary, the mean has to be constant. Now let's go to see what happened with Universal Kriging. Universal Kriging assumes this model and is the same as the other models. But in this case, mu, it's a deterministic function. In most of the cases, this is a polynomial function. For example, in the following figure, which has the same data that was used for the ordinary Kriging concepts, the observed data is given by the solid circles. It's these black dots over here. A second order polynomial is the trend, long dashed line, this line over here, which is the mu. If you subtract the second order polynomial from the original data, you obtain the errors, the epsilon, which are assumed to be random. The mean of all errors, epsilon, is 0. Conceptually, the autocorrelation is now modeled from the random errors, epsilon. Of course, you could have fit a linear trend, cubic polynomial, or any number of other functions. The figure above looks just like a polynomial regression from any basic statistic course. In fact, that is what Universal Kriging is. You are doing regressions with the spatial coordinates as the exploratory variables. However, instead of assuming the errors epsilon are independent, you model them to be autocorrelated. The advice is the same as for ordinary Kriging. There is no way to decide based on the data alone on the proper decomposition. Universal Kriging can use either semivariograms or covariance, which are the mathematical forms you use to express autocorrelation, use transformations, and allows for measurement errors. This is what we did with the data we are working. Remember when we was using the trend analysis with RStudio? We fit a regression model in our data. That one was the groundwater elevation, and this one was the y coordinates. And then what we did is just fit a regression for the linear, for second order, and also for third order, for the y and also for the x. It was this one. And then let me open this one. And then what we did, we assumed this one as a trend, and then we removed this one from our data, making this one 0, and then we work with the values of the residuals. It's the difference between this plane and our data over here. But as you can see, this one is just for one dimension, but we did with multiple regression, working with x and y. The problem of using this kind of model is that you have to decide what kind of polynomial order you want to remove from your data. In this case, it's very clear that it's first order polynomial, but as you remember for the other graph, not this one is for groundwater versus x, but if you take groundwater versus y, As you can see, the second order and also the third order fits really well with your data. Then at the end, the professional have to decide what polynomial is removing from the data, and it's very subjective. The next thing I would like to talk about it is how to calculate the anisotropy properly. I know at the previous videos it was not pretty clear, and now a subscriber give me some tips to improve the experience with ArcMap and calculate in a proper way the anisotropy. Then we are going to select the data here, Kriging, and the next select universal one, no transformation. Here is going to be a first order polynomial and prediction. Next, we know about this screen about the removed data we talked in a previous video. Then here we are going to select the spherical one. Here for anisotropy we are going to select true. And the problem previously it was that I have this screen very small, something like that and something like that. And then when you try to change the number here, when you put true here and you want to change the numbers, you cannot see any number to add, right? But if you make the screen bigger, for example, something like that, now you are going to see the numbers here. Then here you can place the numbers you want, 135 for example, and then you are going to see the experimental semivariogram associated with this 135 direction, right? If you put, for example, 90, the experimental semivariogram is going to change, and also the model semivariogram. Then what I am going to calculate, it's a direction here of 135. Then just press the button here, change the direction, 135, and then select the lag size, 15 meters, and also the number of lags, 15 meters. I know this direction, it's not for the maximum anisotropy, but I would like to see how looks like the Kriging interpolation for this direction. The direction with the maximum anisotropy is given by default when you put here true for this parameter, and the software provide automatically the direction of the semivariogram with the maximum anisotropy, right? In this case, as you can see here, is 94.92. Then here put 94.92, and that's the experimental semivariogram with the maximum anisotropy, right? But as I say, I want to calculate the one for 135. It's this one, then here 135. For the tolerance angle, it's going to be 22.5. And here the maximum bandwidth you can add here is 15 meters. And that is how it looks like the experimental semivariogram, the cloud of points for a direction of 135 degrees, and also the mathematical model fit on the experimental semivariogram. Then here you have the major range is in this direction, 135, and the minor range it's 90 degrees to the maximum, to the major range. It's this direction here, 90 degrees. Then it's going to be 135 less 90 degrees. Then the minor range, it's an angle of 45 degrees. Then just press next. Also we was talking about this screen last week. Then 57 here, 18, and I want just one sector. Then next, that's the cross validation. We know, and we have already one video about the cross validation. And finish, that is the report, where you can see here the model, the range, the anisotropy, yes, the minor range, the direction, what is the partial seal, and all the parameters we added. Okay, and that's the Kriging interpolation for a direction of 135 degrees with a spherical model for the universal Kriging. Now I'm going to export this geostatistical layer as a raster, but we have to follow specific steps to do this job. And if you want to know how to do it, just watch the previous video where I explained already. Now I'm going to pass the video faster. Okay, that's the final result. That's the Kriging we have with the geostatistical layer, and that's the raster I have. Then what I did is first I export this geostatistical layer as a vector. As you can see here, data export to vector. That's what I did. Is this layer here, and then from this layer I pass to a raster file. Is this file over here. Now I'm going to do the same for this one is for a spherical 135 degrees. I'm going to do the same for the universal for a spherical one, the omnidirectional semivariogram, also for the exponential, and also for the Gaussian, all of them omnidirectional ones for the universal Kriging. I know I said as a previous videos that I'm going to compare with the ordinary Kriging with a first renewal, but I decided to do with universal one because that's the kind of Kriging we are using with RStudio. And I believe in terms of comparison, the best is going to be just compared with universal Kriging in ArcMap and also universal Kriging with RStudio. But I'm going to come back when I have all the interpolations completed. I created already all the universal Kriging for the 4 models we are going to compare. Then this one is for spherical 135 degrees. This one is for the spherical omnidirectional. This one is for exponential omnidirectional, and this one is for the Gaussian omnidirectional. Then I created a folder. I created this folder the other day for all the universal Kriging interpolations with RStudio, and this folder is for all the models for ArcMap. Now what I'm going to do is open Quantum GIS, and we are going to compare and edit all the maps using Quantum GIS. First, we are going to start the edition with the maps we did with RStudio. This folder here, and let's go to open all these together. As the maps were geo-referenced with RStudio, the coordinates over here are good. And the reference coordinate systems, let me show you. Properties, information, is this coordinate reference systems. For each of these files, we have 2 maps. This one is the variance one, but if we change the bands, as you can see here, band 1, band 2, if you change this one to band 1, we are going to have the predicted map. Apply. That's the predicted values for the Kriging interpolation. And the other one, it was for the variance. Now what I am going to do is add the data here. It's a vector file. Shapefile is this file over here. Open, add. Then what I am going to do now is a perimeter of all these points, and I'm going to use this perimeter as a mask to cut the raster layer. Then to do that one, just go here, layer, create a layer. Is going to be new shapefile layer. Then the name is going to be the perimeter. Then for this one is going to be polygon. For the reference coordinate systems is going to be this one here. For the rest of parameters is okay. then OK. You have your layer here, then press this button here to edit the layer, and I'm going to select this tool. Then I'm going to select the points, and I'm going to do the perimeter, the exterior perimeter. But I'm going to pass the video faster. Then this is the external perimeter of my data. Then I'm going to add ID, that is going to be 1, OK, and I'm going to edit this one. To finish the edition, just press here, save, and then go here, properties, symbology, and I'm going to make this one transparent and with a dotted line, red color. Apply, okay. And that's the perimeter I have. I'm going to use this perimeter to cut all the raster layers, because in this way I'm going to avoid all the extrapolation area over here, and we are going to work just with the interpolation area. It's the area inside of this perimeter. To do that one, we are going to go to raster, extraction, clip raster by mask layer. Then here select the raster you want to cut. For example, let's go to select the exponential one. Here the mask you are going to use is the perimeter. Here if you want to change the coordinate reference systems, we are going to leave that ones because all the layers are in the same reference coordinate systems. But if you want to change, you can change the target for a different reference coordinate systems, and then press run. Close. As you can see here, it cut the area we want, but it leaves this black area over here, and we don't want that one. Then let's go to remove this one. What you have to do then is the same raster, extraction, click here the exponential one, and then here assign a specific node data value to output bands, then here mark 0. Then we are going to select where we want to save the new file. Over here. Then it's going to be map 2. And here I'm going to create a new file that is going to be clip rasters. Clip rasters RStudio. Okay, then inside this one is going to be the exponential one. Save. And for the rest of parameters, that's okay. Then run and close. When we have this layer, we can edit here the band. Then here this composition, band 1, band 2, is for the variance, and what we want is the predicted values. Then here we have to change for this one, apply, and here we want to add 90.5 to 96.5. We are going to do the same for all the maps, just to make sure that we have the same contour lines, the same range for the contour lines. Then here is going to be discrete, and here is going to be equal interval, and here is going to be 12 intervals. In this way, what we have it's numbers with just 1 decimal. Then apply, and okay. And that's the final map. Let's go to take this one for the exponential one, okay, with the interpolated area. What I'm going to do is the same for all the maps, but I'm going to pass the video faster. I'm going to change the name here just to make sure that we have the proper names for all the layers. This one is going to be for RStudio. For our map, I'm going to add AN. Okay, all the models are already completed. This one is the Gaussian. This one is the spherical. This one is the spherical 435, and this one is the exponential. Now I'm going to add the layers for the ArcMap. Go here. We have to select the raster, then go to the folder. Is maps 2, ArcMap, for example, for the exponential omnidirectional, you have to select this option here, this extension, ADF. Then open, add, and that's the map we need for ArcMap. Then I'm going to do the same for the rest of the maps, but I'm going to pass the video faster. I have already all the maps here from ArcMap. Then what I'm going to do is remove all these layers because I don't need these ones longer. Okay. And now I'm going to cut all these layers also with the perimeter we have. And I'm going to add also the same range and the same colors for all the maps from ArcMap. But I'm going to pass the video faster. Okay, all the models are already complete. This is the exponential one for ArcMap. This is the Gaussian one. This is the spherical one. And this is the spherical one for 135 degrees over here. Now what I'm going to do is remove all these layers. Remove this one. Okay, remove this one also. Now what we are going to do is compare all the maps. As all the maps are pretty similar, it's quite difficult to show the differences between all the models. Then I decided to make a composition with the raster image and also with the mix of raster image and vector layers, and also with vector layers. I believe in that way, making all these kind of different compositions, we are going to see the differences between the models in ArcMap and also in RStudio. Let's go to start with the raster image composition. Then go here, projects, a new print layout. I'm going to put for the name of this composition number 1. Right click on the mouse, page properties, and here I'm going to select A3, and orientation landscape is good. And as you can see, this one it's a big paper, and the reason is because we are going to present here 4 maps for ArcMap, and also here at the other side 4 maps for RStudio. Then what I'm going to do, it's just a rectangle over here, something like that, and then I copy, Ctrl C, Ctrl V, paste. I'm going to place at the same location as this one. I want to make sure there is overlap, a good overlap, something like that. Then I'm going to move this one to the half, right there. Now I'm going to add some labels here for the titles. This one is going to be ArcMap, and I'm going to change the size. Just double click here, select a size, for example 24, even bigger, 28 and bold. That's good. And also I would like to add here Universal Kriging. Then I'm going to make this one smaller, 26, okay. And I'm going to center. And I'm going to place at the center of this rectangle here. Something like this is good. Now what I'm going to do is bring some of the maps here, but first I'm going to take these ones out. I'm going to leave just one, the spherical 435. Go here. and I am going to add the first map just with this option here. Select an area, and I want here for the scale 4000. Then I want to make sure that the scale 4000 fits well in this frame. As you can see, we have to make this one a little bit bigger. Okay, something like that is perfect. Then what I'm going to do now is copy and paste this one. Control C, Control V. Going to place over here. Control C, Control V, one more. And also one more. Now I have to fit these 4 maps. I am going to place a guide just to make sure the maps are at the center. Just take here this one and drop over here at the middle approximately. Right there. And then you have this guide to put the maps at the center. If it doesn't work, just move this option here to the top. Then let's go to edit this one. And I'm going to copy and paste for the rest of the models, but changing the label. Also, I'm going to add a new label for the root mean square error for each model. Now what I'm going to do is copy all of these ones and paste at the other side. Now what I'm going to do is edit all the layers properly, and also these ones here. Okay, this is the result. And now what I'm going to do is edit all the maps according to the model and also the software we was using. At this point you have to pay attention to the detail if you don't want to miss the maps or mix the maps. Then what we are going to do first is lock all the labels that we are not going to use, and we want to that labels to be there without moving. Then it's going to be all the text and also all the rectangles. Then I'm going to pass the video faster. Then we are going to work with the maps. First, let me show you how it works. When you refresh here, that one is going to update what the information that you have here. Then if I select this one and I go here and refresh, I'm going to have this map for all the boxes, right? For all the frames. Now I have 8 frames, as you can see, 4 in this side and 4 in this side. Then to start, let's go to plot this one, the spherical 135 degrees for ArcMap. And I have the label here. Then it's going to be this map. Then select this map here, go here to this box, see what is the map over here. Is the one what is selected, but I cannot see now. Map this one, maybe 1. Okay, just check like this. 4 is this one, number 6. As you can see, it's black over here. Then lock this one here and also lock over here and over here. In this way you are going to make sure that this map is going to be locked and it's not going to change. Now for the next one is a spherical for our map. Then go here, take this one out, a spherical for our map, this one. Then go here, refresh, and what you have here now is the spherical one. Then select this one is number 5. Then lock here, and also lock here and here. And then we can move to the next one. That's exponential one, is number 1. Then let's go to change over here to the exponential one for our map. take this one out, go here, and then refresh here, and then you have the exponential. Select the map here, is this one we set, number 1, then lock here, and lock here, and here. And then I'm going to do the same for all the rest, but I'm going to pass the video faster. Now we have all the maps in a correct position. I have all the layers locked. You can save this print composition, just press this button here to save, and it's going to save here for the number 1. Then, for example, if I close this one and I want to open again, just I have to go here, Projects, Layout Manager, and select number 1. That's the name we put for the composition. Double click, and we have the composition here. Then now I'm going to export. There is different options as an image, as a export as a SVG, and also as a PDF. I am going to export as an image and also as a PDF. Then to export as an image, just press this button here, select the folder, and also select the name. For me, this name is good. Then save, select the parameters, and then save. And here you have the final result. We can open here, open the file, and that's the result. As you can see, the quality, the resolution of the image is really good, but it's hard to compare the maps because they are all of them pretty similar. The first differences is related with the root mean square error. The RStudio provides the highest values for each model, and the ArcMap, as you can see, for example, for the spherical 135, for the root mean square error we have 0.1148, but here we have 0.1630. It's a little bit higher in this part, right, for all the models. But if we compare, for example, all these ones for ArcMap, all of them are pretty similar. As you can see here, for example, for this contour over here, we have the same in all, except, for example, for the Gaussian one, that the contour lines are very smooth. Also for this peak here, we have here, 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 but not for Gaussian one. In RStudio, it happens the same. We have very similar models. We have here this peak in all of them, also this one here, but the Gaussian model is totally different. Also, if you compare the Gaussian model from ArcMap with RStudio, they are totally different. And also the root mean square error here is the highest one. Then in general, if we take the 8 models, for me the best one is the Gaussian one from ArcMap, because the contour lines are pretty natural and they are very smooth. We don't have this kind of peaks that you can see, for example, here, here, and also these peaks here that I don't like too much. It doesn't make any sense. It's pretty unnatural, but for the Gaussian model, the contour lines are very smooth. The one who provides the minimum error is the spherical one for 135 degrees. As you can see, 0.1148 is the minimum value. And the maximum value is for the Gaussian here. If you remember, at the video 7th, we was doing the Semivariogram model, and what we saw here, I'm going to show you. When we try to do the fit the model automatically, let's go to run this one, we have this warning, and it's saying that there is no convergence after 200 iterations. Then try different initial values, just change these values for the nugget, for the range, and for the seal. But after trying to change some of the values, it doesn't provide any result. Then what I did is fit the model manually with these parameters, and that one was the result, right? And this is the values that we have. But as the software didn't fit the model automatically, it means that it's something wrong with the Gaussian model and the software cannot fit the mathematical model, right? But what we did is force the situation with this script here. And the result, I believe, is this result, that it doesn't make any sense, right? It is not realistic, right? And then at the end, what I can say is that all the maps are pretty similar, as you can see, for all the models except for the Gaussian one. Then we couldn't reproduce the Gaussian model with RStudio if we compare the results we get with ArcMap. Now what we are going to do is overlap here the vector layers of this map on this raster image to see how the contour lines are different. But first let me show you how you can export with PDF and how the file looks like. You can select here different parameters, but I'm going to leave these ones by default. Click here, and here we have the PDF. As you can see, also the PDF has a really good quality. And that's it for the raster images. Now let's go to move on to the raster layers. What we are going to do is extract the contours for each of these maps. Then to do that one, let's go to start with this one, a spherical one for 135 degrees for our map. Then go here to raster, extraction, and here and contours. Then here select the layer you want, that one is good. This one is good. Here for the interval, we are going to do the same as we did for the raster layer. It's going to be every 0.5 meters. Then here is going to be 0.5. The label elevation is good. And at the moment we are not going to save the file, we are going to keep a temporary file. Then run, close, and then we have the contour lines over there. Then we are going to edit first the name, rename layer, and that one is going to be a spherical 135. And we are going to make a specific symbology for each of the contour lines. For example, we can make here 0.3, and here, for example, this kind of line, apply. And let's see how it looks like. Okay, that's good. And then I'm going to do the same for all the maps. Then I'm going to take this one out and move to the spherical one for our map. Okay, now I have all the contour lines for all the models. As you can see, it's interesting to see how for the models we export from our map, there is a kind of saw effect because of the pixels, of these pixels. But we can improve the contour lines using an algorithm that can make the lines more smooth. But we are going to see that one on the next video when we make the groundwater flow map, and we are going to be working with the contour lines. At the moment, for this video, I'm going to leave the contour lines like that. But for the models we export from RStudio, the contour lines are pretty smooth. As you can see, this symbology here, it means that the file we have here, it's a provisional one. It's not safe on our hard disk. Now let's go to work with the same composition as before, this one, and I'm going to overlap the contour lines from here to here and the contour lines from here to here. The methodology to create this map is going to be the same as before. What we are going to show here is what we are going to have here in our first frame, for example. Then we have to take care of don't mix the maps and also don't mix the contour lines. First, let's go to work with the first frame. Unfortunately, these frames are not in order. The first one is the number 6, then unlock the layer, select the frame, unlock here this one, and then go here and select what kind of map you want. For the first one, I want the spherical one for 135 degrees for ArcMap, a raster layer, and now I want to overlap the same model from RStudio, but the contour lines is these contour lines over here. Then I have to go up with these contour lines to here to put this one on the top. Okay, then when I have this one ready, I can go here, refresh. Well, it's already refreshed, as you can see. Then lock the layer again, this one and this one, and move to the next one. Number 5 is number 5, but I'm going to pass the video faster. Also, what I am going to do is add the legend for each of the contour lines. Then just select this option here. Now I'm working on this map number 5. Then select a small area here. Then select here only these features, and also take this one out. And then what I want is just to show the contour lines for the spherical for RStudio. Then I have to remove the spherical from ArcMap. Spherical from ArcMap is this one here. Spherical for ArcMap. Then take this one out, and that's the legend we are going to have here. Then place the legend where you want, for example over here, and that's what I'm going to do for all the maps. Okay, now I have all the maps with the contour lines for each model to compare, and now the map is ready to be exported. First, let's go to save the project, and then I'm going to export as an image. In this case, I'm going to add the number 2 for the name. Save. I'm going to leave the same parameters as before. And now the map is ready to be open. Now let's go to talk a little bit about this map. What we have here is the raster image for the spherical model for a direction of 135 degrees for Universal Kriging for ArcMap. And then I overlap the same model, but just the contour lines from RStudio. Then we have to be aware that for the colors, we have this scale I'm going to show you for the spherical 135. Taking this one out. This model here, this is our scale, is from minor or equal to 91 meters, and then to 96 or bigger. Okay. Then that's the colors we have here for the raster image. Also, I would like to mention that for the ArcMap, we don't have the lowest values, because when I export it from the geostatistical layer to vector layer and then to raster layer, to do the exportation, I selected the highest value for each pixel. Then it was not the mean value, it was not the minimum value, because it was possible to choose that options, but I choose the highest value for each pixel. Then maybe we lose some information here at the lowest values for the pixels. That's the reason, because in this image we don't have any value here, but in the other one we have this. Let me make this image bigger. We have this kind of red here that it's a lowest values than the values we have in the other image over here. But in general, as you can see, the contour lines are pretty similar and the models are almost identical. Then let's go to compare with the other one. In this case, what we have is the spherical model for 135 degrees for RStudio for the raster image, and I overlap the contour lines from ArcMap from the same model. And as you can see, the contour lines are pretty similar. The only differences, I believe, is related with the lowest values. and the problem it was related with the exportation from ArcMap. Then for the spherical model, for the omnidirectional one, the values again are pretty similar and the contour lines are almost identical. If you can see from here to here, they are identical, right? The only differences is over here and over here. Here we have more or less the same result. And now let's go to move to the exponential one. We have again the same results, pretty similar. And also here, pretty similar, the contour lines and also the raster image. But for the spherical, I mean for the Gaussian one is where we have the maximum differences, right? It's interesting to see how these contour lines, they match, right? But from here, they change totally. The same happen over here, right? We have these contour lines that they are matching really well, but not for these ones. And now what I'm going to do is just one composition, but in this case I'm going to compare just the contour lines for ArcMap for all these 4 models and also for RStudio for all these 4 models. But it's going to be just with vectorial layers. To do that one, I'm going to create a new composition. I'm going to save this one and I'm going to close. Go here. It's going to be project. New print layout, and this one is going to be number 2. Okay, and what I want to do here is take this one out and just select the contour lines for the ArcMap. AM is ArcMap. Okay, that's the contour lines. I'm not sure if the map is going to be a good one. It's not going to be very clear, but let's go to try. Then go to the composition, click right, and for this one I'm going to select A4, that's good, and I'm going to bring them up. Well, first I'm going to make a box here. And I'm going to lock this one. And I'm going to bring them up. Something from here to here. Let's see how it looks like. And let's see the scale, for example, 4000 is going to be very small, maybe 3000. Something like that could be good. I'm going to adjust this one a little bit. Maybe smaller here, 3000. Okay, maybe that one is good. Yes, I believe something like this is going to be good. I'm going to add a frame here, frame, and I'm going to move this one a little bit over here, and I'm going to add the legend over here. But I'm going to select only the ones I want. It's going to be just the contour lines. Over here, and I'm going to copy and paste this one here, but I'm going to make this one smaller, take this one out, Ctrl C, Ctrl V. Okay, both now are the same. The legend. Okay, I'm going to take this legend. I'm going to move this one a little bit inside here. Okay, add the legend. But I want only these ones. Over here, and now I'm going to add some labels here to indicate that that one is from ArcMap. I believe it's not the best map, but it covers the purpose of this map, right? Then I'm going to add here a label for the legend. I'm going to lock this map here, and also I'm going to lock the legend and the titles. Now I'm going to modify this one, but first remember that we have to lock also these ones here. Okay, that's good. Now I'm going to modify this one, but I'm going to move this one a little bit. Okay. Take these ones out, and then select for RStudio the contour lines. And let's go to update here. Going to move the map a little bit. Okay, something like that, and I'm going to add the legend. I'm going to save, and I'm going to export the image. That's a number 3. And I'm going to open now. And let's go to talk a little bit about this image. As you can see, for the results for ArcMap, all the contour lines are pretty similar for the 4 models. The only one it's a little bit different is the Gaussian one, because the contour lines are more smooth. But for the spherical, for both, for the omnidirectional and for the directional, and also for the exponential, the contour lines are pretty similar. Then for the RStudio, as before, the problem is related with the Gaussian model that is doing something really weird. But for the rest of the models, for all these 3 models, the spherical one directional, the spherical omnidirectional, and the exponential omnidirectional, the contour lines again are pretty similar. Okay, that's the end of this video. Thank you very much for watching, and see you on the next one, where we are going to decide what model we are going to choose to create our groundwater flow map direction, where we are going to create all related with the groundwater flow map.